Hello everyone, welcome to another processing video. So this time I'm going to do a vector field simulation. And what is a vector field? Well, basically it's an idea from multivariable calculus where you have a 2D plane on which there are vectors at every single point, and those can be used to kind of define the forces on the field. Like, for example, if you had a ball on some sort of point, then it would get pushed in some direction. And then when it gets to its destination, or wherever direction it's going, it'll have another force applied, and that force will be different or the same, I don't know. But it all depends on the vector field. So something like F equals, and then you have the kind of pointy brackets, let's say y negative x. And that is kind of like a hurricane kind of shape. Let me see, this shape would go counterclockwise, I'm pretty sure. Wait, so at 1, 0, it would be 0, negative 1. Okay, so actually this shape goes counterclockwise in a kind of circle. So the force is kind of like a hurricane in the southern hemisphere. Because in the northern hemisphere, hurricanes actually go counterclockwise. But if you wanted to go counterclockwise, I think this is what you would do. What do you think? Yeah, this seems about right. Because at 0, 1, you would have negative 1, 0, and that would go left. So that would be, yeah. Alright, so anyway, let's continue with the program. So what I'm trying to do is utilize p vectors to push some balls around on the screen. And then if you spawn enough balls, you'll be able to actually see how the vector field functions. So this should be a very interesting visual effect. Alright, so we have setup and draw. We actually need a class of balls, so we'll make that here. Whoops. Alright. We got balls there. That's a constructor. We'll make some p vectors for it to use, and we'll use just position and velocity. Alright. So p will be equal to random. Hold on. New p vector. Random. Okay, we'll have to go from negative width over 2 to width. And you'll see why later. I did write this program before. I planned it out. And we'll be doing a translation so that the center of the screen will be 0, 0. And so we won't have any of the weird processing coordinate plane messing us up. So in draw, we have to do like a push matrix and a pop matrix at the end. So yeah, let's make an array list. Array list. Hold on, I think I did this incorrectly. Okay, so this should be just ball with a capital B. And balls will be here. Yeah. Oh wait. Ball equals new array list ball. Okay, and then in setup we can do a for loop from like 0 to, let's just do 500. We can adjust that later. And balls dot add new ball, And then velocity will just be a new p vector 0, 0. Alright. So at this point, what we can do is do some display function, void move, and that should be good. Alright. And then in draw, of course, we have to do for ball b in balls b dot display. Or I think we can move it first, maybe? I don't think it matters. Yeah. Okay. So for display, we'll just do fill. We can fill with a random color. Random 100, 200. Random 100, 200. And then we draw a circle. So for the circle, we'll have to draw it at the p.x, p.y. And then the size, we'll just make it like 20. And then for the move, this is the actual interesting part. We'll do v equals new p vector. And this will basically just be like using the vector field. So the function of our vector field, let me write it down here. It'll be f equals cosine y and sine x, I'm pretty sure. And that will make like a whirlpool effect where there's a bunch of whirlpools. So you'll see what I mean. So cosine of the y value, which is going to be p dot y, and then sine of p dot x. Of course, this may be wrong, and I can fix it later. So the effect will be better. And then p dot add v. So I think this should be able to function. We'll see. Let's just run it. Oh, wait a minute. Okay, so I have to draw a background. Background will be let's just make it white. Oh, and the color. Yeah, the color cannot change. So it's actually just flashing different colors. Just make it white. Okay, so some of them are not moving. Then I must have done something wrong. So let's see. There might have been another function. I think it's apply force, but actually it doesn't do much. What is going on? Let's see. Guys, would you like division? Divided by 10.0. Huh. Okay. This is nice. Oh, I never translated. Okay, so this is really dumb. And I did this wrong. So when we do this, we have to translate width over 2, height over 2. Okay, this is the desired effect. So you can see they're all going in a kind of grid pattern. And so originally there were quite a few in strange locations, but now as time passes, you can see they form these kind of crosses. So they go to one of the points and then they pause and then they go to the next point in their rotation. And if you decided to look at any one of these balls, then you could track them and you would see that they actually just move in a kind of square shape. So that's very interesting, I would say. Oh, and they go off the screen? I'm not sure, I wasn't checking. I think they go off the screen and then they come back on. Okay, that's interesting. So you can see this is quite a nice visualization. It looks pretty funky. And you could introduce a bit of noise. So let's do p dot add v dot rotate, and we can do some tiny amount of like noise. So let's just do a random number. Random -2 to 2. Okay, now they're going crazy. I'm not sure I like this. Yeah, it's kind of weird. So let's just not do that. But this program does look pretty nice. It's like they're all in some very turbulent water. They're kind of jiggly. Not sure why. Alright, let's try to increase the scale. Or I guess like zoom in a bit, I mean. So let's do this. Now you can see they're moving in bigger circles. So the grid will appear to be more zoomed in. Yeah, this is pretty nice to look at. So now you can see the grid is kind of like here. Here's one diagonal. Here's the next one. Here's the next one. And it goes like that. And the other direction, they go like that. So that's very interesting. Okay, so this is a nice vector field. Now, what if we did this one that I mentioned? Well, let's just try it out. See what happens. So let's do the -y. Okay, so you can see they're all going clockwise. So that's probably because, hold on. If you go -y, that means, hold up. Oh, I think processing is like backwards. Yeah, because processing, the bottom right is actually the positive quadrant. So if we just rotated it, rotate pi. Okay, that's just not how it works. But the point is, processing is kind of like flipped from the normal coordinate plane of x and y that you would use in math. So when you do -y, it actually goes in the clockwise direction. But now what if we did like some if statements where if you go off the screen, you'll wrap back around? What would happen in that case? So actually, it wouldn't work so well for this example, but if you just look at it right now, it's pretty fun to look at. Cool. Alright. If you have any ideas of your own, then feel free to share in the comments or make your own video. I don't know. But yeah, now they're kind of just rotating. And you could achieve this effect with the rotate function. Or actually, no, you couldn't. You cannot achieve this effect with rotating in just the matrix. Because you can see that these are actually going outwards. And pretty sure that's because when you go further away from the origin, the actual vector that you get has greater magnitude, which means you fly further away, or farther away. And you can see there's only one left, and he's accelerating outwards. Yeah, he's gone. Yep. Okay, they all left. You could use a wrap function. Let's try it. So, if p dot x is less than 0, or less than width over 2, then we set p dot x equal to, wait, no, it should be negative width over 2. And we can just write them all on the same line. Okay, so greater than width over 2, we'll set it to the negative p dot y is less than height over 2. P dot y will be equal to height over 2. If it's greater than height over 2, then we set it to negative with height over 2. Okay. So I think they are actually wrapping around. You can see there's a lot gathering on this kind of corner, on these corners. So I think this is pretty strange. I guess when you go past that point, you can't really get back in, but I'm not entirely sure if that's how it works. Yeah, they are all gathering there, mostly. There are some further out. But this is a cool effect if you were trying to do some sort of game where you get to control the people and like just throw them around all over the place. Like if you had a village and then you applied various forces, this could be one of them. Although I'm not using any forces here, it's just I'm changing the velocity using this vector field method. So I'm just straight up setting it equal to whatever it should be. If you were going to apply a force, then what you would do is actually have an acceleration here. A would be equal to this, so we can take that away. Then V dot add A. Oh wait, I need to add this vector. And then A equals new B vector 0, 0. Alright. So this should make it kind of more interesting. And we have to limit V dot limit, like, let's do 5. And P dot add V. And we have to reset A, so set magnitude 0. Or I guess this actually wouldn't be an accurate kind of force, because you're just sort of setting the acceleration, but this does the same thing. So if you were going to do like an apply force method here, then you would do apply force, and then it would take a p vector as an input, and then acceleration would be changed by some amount. But anyway, we don't actually need to reset A because we're not using forces that are continuously being added on to our ball. Okay, so you can see that when you use acceleration, it's kind of like, I don't know what this is like. This is like kind of moons orbiting around a planet. Kind of reminds me of Saturn. You can see because acceleration is increasing, it's just getting further out. And how would you change that? Well, what you could do is instead of basing it on x and y, you can make it a constant. So let's say you had 20. 20 is too high actually. Let's do like 2. And then p dot x divided by 20 would actually be just -2. So let's see that. Oh wait, that's not functional. You'd have to do y divided by y or something. I think y divided by... No. You do y and -x, p dot y, and p dot negative p dot x, and then you would have to do some transformations or scaling. A dot set magnitude. What would it currently be? Currently the magnitude would actually be p dot y squared plus p dot x squared. So we would do just set mag to 1. So we would directly set the magnitude, and now you see everything is kind of accelerating towards the same place, and that's not the effect I wanted actually, because this looks kind of horrible. Okay, now it looks kind of decent. Doesn't look too bad. I mean, it's not what I wanted, but sure, I'll take it. So this is kind of the problem with acceleration. Basically, it's just everything just converges. So if you were to do this, probably set the magnitude. What I actually do? Because it can't be constant. And it can't be too little, or else they'll converge to the middle. Yeah, now they're just converging to somewhere that's like closer in the middle. Oh, actually they're not. What are they doing? Oh, we can just wait here, I guess. They'll expose themselves soon. I don't think they're converging actually. Oh, yes they are. Wait, are they? I'm kind of seeing them go outward when I focus on the middle of the screen. This is recording, right? Okay, it is. Great. So I guess this does work if you're trying to do something like this. Maybe you would want some normal force with the walls? I don't know. You can add that on your own. Normal force is simply the opposite of regular forces. Whoa. Oh, that's not what I meant. It means a force that goes opposite of a surface, basically. I like this shape. This looks kind of like, I don't know. Looks like a Tide Pod. Alright. That's a throwback. Can't believe I even said that. So I think the ones here are going up, and then they're going back down. So all of them are kind of just going horizontally, and then going back where they were. What if we did like a dot divide 2, 2? Oh, it's a p vector. P vector 2, 2. New p vector. What? I don't even know how divide works. So we'll just not do it. But you can see how it might be kind of interesting. Or I think maybe a dot limit would do something interesting. Wait, what if we limit it to like 10? Okay, so it can't go any higher. That means the ones on the outside can't go faster than the ones on the inside, and the ones on the inside are going really quickly. Are they expanding outwards? We'll see. Okay, so the answer is yes. They are expanding outwards. But when are they gonna hit the limit? I think they did hit the limit. Yeah, I guess even if you set the limit to 10. Oh, 10 is just right there. Okay, I see. So what if we did like 5? Okay, so now I feel like they're gonna converge at somewhere close in the middle. Yeah, they are. What is even going on? Okay, what if we limit it to 3? I mean, velocity is already limited, so I don't think it's gonna do much. Wait, what if like it was just 2? The ones on the outside are going closer to the inside. Is interesting. Okay, so this isn't really doing much for me. This is literally just setting the magnitude. It's like the same thing. There's no point in doing this. Oh, this shape reminds me of the one where I did, I think, 0.3 or 0.5. I think it was 0.3. But I do like this, so we'll just do a dot set mag 0.2. Yeah, this is interesting. Okay, what if we went back to the cosine y and then the sine x? Whoa, what is happening here? This is cool. Oh, I see. Okay, so when you do acceleration instead of velocity, you get this effect where once they're on the edge, because this is kind of like a whirlpool combined with other whirlpools. So if you were doing a velocity field, they would eventually go to the outside of the pools and then just keep moving like that in cycles. But if you do this thing where it's acceleration, they will stay in the fast lanes where they just get pushed in one direction. So if you look for the horizontally moving ones, they are just moving continuously because they're getting pushed along by the edges of these whirlpools here. What if we didn't limit it at all? Alright, so there's not much of a difference because we are limiting the velocity. What if we didn't though? Oh, they're gonna spaz out. Yeah, this looks insane. I don't really like it. What if we just had 100? I don't like this either. Okay, what if we did have a limit and v dot limit 4 semicolon. Yeah, they're just doing the thing I was talking about. They just stay in the fast lanes or whatever. So not that cool, but if we go back to the velocity thing, where v equals this. Alright, these are too small. So 10.0. Oh, divided by 0. Okay. And then what about 20. And if we had 500 of them. Okay. So we're back to where we were. Yeah, I guess this is about it. B dot limit, of course. Hold on, there was something else I wanted to do. Okay, what if like one of them was negative? Oh, they just go in the opposite direction? What about like this way? Now they go clockwise. Okay. What if I didn't do anything? They go counterclockwise. Wait, do they? Some go counterclockwise, others go clockwise. Okay. Is that true for the others as well? I don't know. But it's not important. So yeah. Thank you guys for watching this video. And see you guys next time.